Okay, this is sample problem 6.5. Calculate the de Broglie wavelength of the particle, in quotes, in the following two cases. A 25-gram bullet traveling at 612 meters per second, and B, an electron with a mass of 9.109 times 10 to the minus 31 kilograms, moving at 63.0 meters per second. Okay, so this is the de Broglie wavelength, so that's the wavelength of, quote, particle, something that we think of as a particle, is equal to Planck's constant, h, over the momentum, which would be the mass times the velocity of this, quote, particle. Now, it's important when you do these problems to have everything in the MKS system of units. So the mass under the MKS should be in kilograms. The velocity, or the speed, should be in meters per second. And then Planck's constant is already, Planck's constant is already in joule seconds. But keep in mind, a joule is 1 kilogram meter squared per second squared. So if you cancel out one of the seconds, that means that 1 joule second is a kilogram meter squared per second. Okay? So let's go through it. We've already got h, so h, you may not remember the value, you got to look it up. 6.626 times 10 to the minus 34, again, kilogram meter squared per second, right? So that's the units of h. Divided by, now we're doing part A. So part A is 25 grams. So a kilogram is 1,000 grams. So this would be 0.025 kilograms. So I'm going to put that in here, 0.025 kilograms. And then the speed is already in the MKS system. It's already moving at 612 meters per second. So let's go through the dimensional analysis. Kilograms cancel. One of the meters up here cancels with the meter down here, and the seconds cancels with the seconds there. They're both in the denominator. So you're just left with meters. So the wavelength is going to be in meters. Okay, so let's 6.626 times 10 to the minus 34 divided by 0.025 divided by 612. Whoa, for some reason that didn't work. 6.626 times 10 to the minus 34 equals, there we go, divided by 0.025 equals, oh wow, now that's sort of odd, I don't know why that happened. 6.6, let's put this in parentheses maybe. 6.626 times 10 to the minus 34. All right. Divided by 0.025. Okay, so this calculator doesn't really want to do it. Okay, so let's try it this way. 6.626 divided by 0.025 divided by 612. And you get 0.433. Okay, now we just have the 10 to the minus 34. Now we want to put that in scientific notation, move this over 1, and you get 4.33 times 10 to the minus 35. Okay, so there's your wavelength. Now, they don't ask you to consider this answer in any way, but it turns out that that is so short, much shorter than any electromagnetic wave. The shortest wavelengths in electromagnetic waves are gamma rays, and they're around 10 to the minus 12, maybe 10 to the minus 13 meters. This is so short, it does not correspond to any electromagnetic wave. And so what we would say is that if the wavelength of the electron, well, this is a bullet, not an electron, so let me erase that, of the particle is less than the wavelength of a gamma ray, then it's a classical particle. Meaning that it does not behave as a wave. It acts just like a bullet. Okay? So for that reason, a bullet cannot undergo diffraction or constructive interference or destructive interference or many of the properties that we consider when we consider waves. Okay? So that's part A. It's going to behave classically because wavelength is so short. But let's take a look at the second one. The second part B is the electron. So the wavelength of the electron is going to be, again, h, 6.626, times 10 to the minus 34. Again, kilogram meters squared per second. Okay, because we canceled out the seconds. And then we're going to divide that by the mass. Now look at this mass. See how small this mass is? It's so small it's going to make the wavelength not so tiny, not so short. And again, this is 63 meters per second. Okay? So let's take a look at this. So 6.626 divided by 9.109 divided by 63. So 6.626 divided by 9.109 divided by 63. And it's 0.0115. But we have this 10 to the minus 34. And oh, I made a mistake down here. This is minus 31 is the mass, not 34. Okay? So here we have two powers of 10 that we have to consider. 10 to the negative 34 divided by 10 to the minus 31. Now let me show you how one way to deal with this. If I do the following, if I multiply this by 10 to the minus 31 over 10 to the minus 31, right? That's 1, right? So I'm not changing anything, except that you're going to change the way it looks, because here's what happens. This 10 to the minus 34 times 10 to the minus, actually, I'm sorry, let me change this. My apologies. Okay, let's just make it positive 31. There we go. Good. 10 to the 31 over 10 to the 31. So here's what happens. 10 to the minus 31 times 10 to the 31 is 10 to the 0, because when you take 10 to the x and you multiply it by 10 to the y, it's 10 to the x plus y. Now, why is that true? Well, think about it this way. Suppose I take 100 and I multiply that by 1,000. Well, this is 10 to the 2. This is 10 to the 3. What happens is, if you take 100 times 1,000, you get 100,000, right? And if you move the decimal place over to get it into scientific notation, you get 10 to the 5. So it's really equal to 10 to the x plus y. So the same thing here. 10 to the negative 34 times 10 to the positive 31, negative 34 plus 31 would be negative 3. So this would be 10 to the negative 3. And then in the denominator, you would have 10 to the negative 31 times 10 to the 31. Negative 31 plus 31 is 0, so you get 10 to the 0. But by definition, 10 to the 0 is equal to 1. So this just becomes 10 to the minus 3 over 1, which is just 10 to the minus 3. So times 10 to the minus 3. Now I can move this over a couple more places and get 1.15, and it'll be times 10 to the minus 5. Okay? Again, this is in meters, so let's put the units down here. Okay? So then we ask ourselves, okay, if it's 1 times 10 to the minus 5 meters, where does that correspond in terms of electromagnetic waves, right? The wavelength, if it corresponds to a wavelength of electromagnetic waves, at least in terms of diffraction, this electron would behave similar to that. So if you go back to your first section of this chapter, we talked about the electromagnetic spectrum. And so this is roughly 10 to the 4th nanometers. So it looks like it's in the infrared. So this is approximately 10 to the 4 nanometers, which is in the infrared. So we would expect that the electrons that are being accelerated to 63 meters per second would have at least some wave-like properties that are analogous to or close to that of infrared radiation, infrared electromagnetic waves.